Welcome to Unit 2 of Grade 11 Academic Math. This unit's going to focus on quadratic equations and their applications. And this first lesson, lesson 2.1, is on solving quadratic equations, but focusing on two more methods. So if you remember, back in Unit 1, lesson 4, we reviewed how to use our factoring skills to get a quadratic equation into a factored form, and then use the separate factors that we find to try and figure out what special values make the left side equal the right side, or solve it. But factoring a quadratic is not the only way that you would have learned last year for solving it. So we're going to use this lesson as a way to review what you would have learned last year and also take it a little bit of a step further. So for this first section, we're going to see that some quadratics can be solved simply using inverse operations, which is just the same way you would have learned how to solve an equation all the way back in grade 9. Because we're just trying to isolate the variable, and so that it appears only once. And now you see this strange looking collection of symbols at the end of this. So what this means is the x there is saying that x is going to be an element of the complex numbers. So the x there just represents the x values that we're looking for. This little symbol in the middle here that kind of looks like an E is actually the Greek letter epsilon, but it's used to mean something is an element of or a member of a larger set of numbers. So here we're trying to say that x is going to be a member of or a part of a larger set called C. And capital C is a special letter that we use to represent all of the complex numbers. Remember that complex numbers also include just basic old real numbers as well. So sometimes our answers or our x values that we find will just be regular real numbers, the same way that you would have found those real numbered answers back in grade 10. Sometimes, though, they might actually have an imaginary portion to them, or they might be completely imaginary. And so that's why we're going to look for answers not just that are real numbers, but are elements of the entire larger set of complex numbers. That's all that fancy stuff means at the end. So let's see how that's going to work out. So we're trying to use opposite operations to isolate x for this first example. Well, first we need to get rid of the plus 36. So let's just rearrange a little bit and say that x squared could then equal negative 36 if I subtract 36 from both sides. So where do I go from there? Well, when I've got my variable being squared, I can cancel out that operation by square rooting. So when I square root on the left side, I'll be left with just x. That's what I was going for. I've isolated now. But I have to be really careful with what's happening on the right. So I've taken the square root of both sides. But when I take the square root of both sides, when I take the square root of something, I need to put this little symbol, plus or minus, in front of the square root sign. Now, you might already be thinking about some things that we could do with that negative 36 underneath the square root sign, but before I even get to that, let's just talk about this plus or minus. The reason why it could be positive or negative, and that's really what the plus or minus means, it means we could have a positive answer or a negative answer, is because when we take a positive or a negative and then square it, we get a positive answer. So really, either the positive or the negative form of the original root could have been what we started with. And so whenever we square root something, we have to imagine that our answer could be the positive version of the square root, or it could have been the negative version of that square root. So we will have two different possible values, one being positive and one being negative. But we also have a negative underneath the square root sign. So we definitely know that we can square root 36, but we have to remember the skills that we learned at the end of our last unit to know what to do with that negative. But hopefully, if you think back to what we did last unit, you'll realize that it's really just going to be plus or minus 6i is the way that we would write that. Square root of 36, remember, is 6. And then to deal with that negative, we realize that the square root of negative 1 is simply just I, the symbol I. So what this really means is that x is equal to positive 6i, or x could be also equal to negative 6i. And so that is technically true, but really all you need to write down is this version of it, because that's what the plus or minus symbol really means. It means you actually have two possible solutions. Let's try another one. Now keep in mind that example was enough to hopefully indicate to you that we are taking this a step further than we would have last year. We're not just looking for real numbered solutions, we're actually trying to find complex ones as well, ones that include possibly imaginary parts to them. But that won't always occur. Sometimes we will get real number answers, and let's see an example like that. So here, once again, I'm going to start rearranging. Well, I could keep the negative 2x squared on the left side and make it equal negative 24 on the right. Then I would divide both sides by negative 2. So x squared then is equal to, well, that's positive 12 when I take negative 24 and divide by negative 2. And now I need to do that square root thing again. So x is what I get on the left side, but on the right side, I don't know if the answer I'm looking for is the positive version of this or the negative version of this, so I have to accept that either could be a solution here. But no matter what, it's going to be either plus or minus the square root of 12. So technically I found an answer here, but of course we always want our answer to be in the most simplified form we can find. So let's use the skills that we learned in our last unit to say that in a simpler way, this would really be plus or minus 2 root 3. And we want to make sure that we write it in that way rather than just writing down some decimal value, because if you remember, the decimal value that equals this would be an irrational number decimal expansion, which means its decimals would just go on infinitely. And so at some point, we would have to just round our number off. But if we write it as plus or minus 2 root 3, that is literally indicating the exact value of our answer. Just the same way that you can't write out the exact value for pi by writing out a whole bunch of number digits. At some point, you have to round off. Maybe it's 3.14 or 3.1415 or something like that. But you need to round it off somewhere. So we write down the symbol pi to literally equal exactly the value of pi. And here, when we write down 2 root 3, we're indicating the exact value that we want, not some rounded off decimal number. Let's try this one more time. So sometimes we can still use these inverse operations for something that's more complex, but what makes this possible to solve using inverse operations is that even though it's a more complex looking situation, we still have our variable appearing in only exactly one place. So as long as that's the case, which you can also see was the case for questions A and B, as long as our variable only appears in one place, then we know we can still use inverse operations to solve. Let's first get anything that's being added or subtracted on the left side, try and get rid of that. So I'll leave the 36x plus 2 squared here, and it's equal to positive 4 on the other side. Now I'm going to divide both sides by whatever's attached to my bracket. So x plus 2 squared, I've divided away the 36, and now I take 4 and I divide it by 36, and I could write it down as a decimal, but it actually works out to a nice simplified fraction of 1 over 9. So let's keep going from there. Now, I want to get my bracketed part all by itself. So if I want to get rid of the square that's on the outside of that bracket, I just square root on the left side. When I do that, I'm just left with x plus 2. But of course, I have to square root on the right side as well. Well, that's going to give me plus or minus the square root of 1/9, which is really just 1/3. Write that 3 a little clearer. So the square root of 1/9 is positive or negative 1/3. And again, it's got to be positive or negative, because if I took positive 1/3 and squared it, I get 1/9. But if I took negative 1/3 and squared it, I would also get 1/9. So either of those makes this equation true still. But where do I go from here? Because I don't care what x plus 2 is equal to, I need to know what just x is equal to. But the stuff I have on the right side has a plus and a minus. So I can't really do any more calculations with all of this at once. This is the stage where you're going to actually want to break this up into 2 separate situations. One of the situations says that x plus 2 could equal the negative result, negative 1/3. So in other words, if I then subtract 2 from both sides of that, x could be equal to, it ends up being negative 2 1/3. Oops. Because I'm already at negative 1/3, then I go 2 units farther into the negatives, and so it's negative 2 1/3. You can think of it that way. But then I need to deal with the other situation and say, or the following could be true. X plus 2 could be equal to positive 1/3. And if that's the case, then it's really like x and I have 1/3 and then I'm subtracting 2. So I'm going to think of that as subtracting 6/3. So x would be negative 5/3 in that case. So either of those two values would make the left side equal the right side, so those are our two solutions. And again, just keep in mind that this bigger step that we've taken forward now is that we're looking for solutions that aren't just possibly real numbers, but also possibly even complex numbers that include only imaginary parts or partially imaginary parts. And that's what we saw for question A specifically. Now, when our variable appears more than once, this method no longer works. So if our variable appears more than once in a certain situation, then we could try and factor it, and some will be able to be solved by factoring, just the same way that we use those skills in lesson 1.4. But if it doesn't factor, and we can't use the inverse operations, thankfully, we have a special formula that helps us with those types of quadratics. And because it's a special formula that helps us to solve quadratics, we call it, very creatively, the quadratic formula. So if you remember, it's a special formula that helps us find the x values that solve a quadratic equation. And it says that the x values you're looking for always follow this big rule here using b's, a's, and c's. And those a, b, and c values come from the written standard form of the quadratic equation. So before we use the quadratic formula at all, we need to make sure that we can write the expression, or sorry, the equation in standard form, meaning that everything is all together on one side and 0 is on the other, and we need to clearly be able to see what are the a, b, and c coefficients when that's the case. Now also keep in mind that when we do this, we're not just going to be looking for real numbered solutions like you would have last year. We're going to also accept solutions that are complex numbers or have some imaginary portion to them. Let's see how that works. Well, this is the first one that we're given. And right away you might be thinking, this is weird because I thought we were focusing on quadratic equations, and this doesn't look like a quadratic equation at all. I don't see any squareds anywhere, and it's definitely not in any sort of standard form. But what we want to do is start to simplify this in some way and try and get it into a standard form where everything is together on one side and 0 is on the other, and ideally, we don't have any denominators at all to deal with. That's the key. We want to first try and get rid of denominators. So if you look closely, of course, you realize this is a rational expression, so it's got a numerator and a denominator. What I'm going to do to try and get rid of that is do a cross-multiplying trick. So I'm going to think of my left side as a rational as well. I'm going to think of it as x minus 1 all over 1. Remember, we can turn anything we want, any whole number, into a fraction. So we can turn any expression into a rational expression by just putting it over 1. And from there, what I'm going to do is take this x minus 1 and multiply it by this x minus 1. Then I'm going to take this number 1 on the bottom, and multiply it by this 2x plus 3 that I have on the top of the right side. So actually, I'll maybe just write a little note that that's what I'm doing, and you can make a little note for yourself. I'm just doing a cross multiply step. But what does that give me? Well, oops, don't want to start with an equal sign. I don't need one. I'll put it in the middle. It's going to be x minus 1 times another x minus 1. That's why I made sure I kept those in brackets. And then it's just 1 multiplied by 2x plus 3. So you might even realize that in my next step, I'm just going to be able to get rid of these brackets on the right side, and it'll just be 2x plus 3. On the left side, though, I've got some expanding to do. So when I multiply all that out, I would get x squared, and then after a little bit of simplifying, you'd get x squared minus 2x plus 1. And on the right side, as we mentioned, we just have 2x plus 3. So now, hopefully you can see where we're going with this. We've got something that's clearly quadratic, and we've got truly a quadratic equation now, but it's not something we can use the quadratic formula on just yet because it's not in its standard form. So we need to move everything to one side so that we have 0 on the other. I'm going to take everything that I have on the right and subtract both of those terms on both sides. So in other words, x squared minus 4x now is on the left, and then minus 2. And that's all equal to 0. So with that in mind, that means my a value is equal to 1. My b value is going to be equal to negative 4. Careful, the negative in front's important. And the c value, once again, be careful of the negative, is negative 2. Those are the values that get substituted in to my quadratic formula. So let's see where that takes us. Quadratic formula says that the x values we're looking for are equal to negative b. So right off the bat, I need to put a negative in front and then stick my b value in brackets. That's why I have to be careful here. It's actually going to be negative of negative 4. So in my next step, that whole first piece is just going to become positive 4. Plus or minus, and then I have a great big square root with a bunch of stuff happening inside. Specifically, it's b squared. So negative 4 squared. Notice how I'm using brackets every time I substitute something in, just so that any negative signs, I can be careful with them and make sure that I'm squaring them properly or multiplying them out properly. So keep brackets as much as possible. And then it's subtract 4 times a, which is 1, and times c, which is negative 2. That whole thing we can't forget, and when I say the whole thing, I mean everything that we have there, in our very last step is going to be divided by 2 times a, which is 2 times 1 in this case. So let's start simplifying. It's going to be positive 4 plus or minus. Well, if I do a whole bunch of calculations of everything that I have inside that square root, I would just get positive 24, because it would be 16 plus 8. And all of that is over 2. Last year, you would have just put all of that into your calculator and come up with a decimal answer that we round off. But now, as I said, we want to be able to try and come up with an exact solution if we can, which means we want it to possibly just include the square root symbols themselves, but not any rounded off decimal values. So let's take what we have here and just try and write it in the simplest possible form that still possibly includes radicals in it somewhere. Well, 24, using skills from previous units, I can rewrite the root 24 as 2 root 6, because 24 is 4 times 6, and then I can square root the 4. And then that whole thing is all over 2. But from there, I can also recognize that I can common factor out a 2 on top. And the main reason that I would want to do that is so that I can reduce it with the 2 that I have on the bottom. I can divide each the top and the bottom, or in other words, everything on top and bottom by 2. So my final simplified form of all of this is that, and actually maybe I'll just write a separate statement here. I can say, therefore, x must be equal to, I forgot my minus sign there, 2 plus or minus root 6. Let's try another one with the quadratic formula. Now, in this case, you're probably a bit more confident right off the bat that this will be a quadratic, but we still are running into a similar situation where we've got some fractional things involved. We've got some denominators. So it's going to be really hard to actually put any of this stuff into quadratic formula right now until we get it into a nice standard form where all of our coefficients are whole numbers. Not only that, we want them to be all on the same side together, all of our terms together, and 0 on the other side. Well, I can get rid of fractions in something like this if I take the entire equation, or in other words, everything on both sides of the equation, and multiply it by some common multiple of the denominators I have. So if I have denominators like 2 and 3, they have a common multiple of 6. So I'm going to multiply everything on both sides, that's really important, by 6. So after a little bit of reducing, this is really more of a grade 10 skill. We reviewed this in grade 10, but after a little bit of reducing, you'd end up with 3x squared plus 2x. And on the other side, the negative 1 has to multiply by 6 as well, and that would equal negative 6. We need everything to be together on one side though, so in full standard form, it would look more like this, where now I'm going to add the 6 on the left, and it disappears on the right. What does that tell me? Well, it tells me that A is equal to 3, B is equal to positive 2, and C is also positive, it's equal to 6. Let's substitute in. The x values I'm looking for then are going to be negative 2 plus or minus square root of 2 squared minus 4 times 3 times 6. And that's all over 2 times 3. So it's going to be negative 2 plus or minus. On the inside of this bracket, it actually works out to negative 68. And then that's all over 6. So last year when using the quadratic formula, this is where you wouldn't have even tried to use a calculator. You would have just actually stopped there and said that this has no solutions. But we weren't being 100% honest last year when we told you that this meant there was no solutions. Really what we meant at the time was that there are no real numbered solutions. Again, it means no solutions that would exist somewhere on a regular old number line. But there could be complex solutions that have some imaginary part to them, which again, still means they have some mathematical value, so we still want to find what those values are. So let's simplify negative 68, if possible. Well, 68 is actually 4 times 17. So that's going to help me reduce that radical. I'm going to call it negative 2 plus or minus 2I root 17. Because we know the I comes from the fact that there's a negative under that square root, and the 2 that's in front of that comes from the fact that 68 broke up into 4 times 17, and then I square rooted the 4. And then that's all over 6. Now it looks like I'm just about there, but I look at what I have on top, and I can do a little common factor again, just like I did in my previous one. So I'll common factor out a 2, leaves me with negative 1 plus or minus I root 17. And that's all over 6. And the reason why that's useful to me, of course, is because now I can divide the top by 2 and leave a 1, and divide the bottom by 2 to reduce it to a 3. So now in the end, I have negative 1 plus or minus I root 17 all over a denominator of 3. And that is the simplest way that I can write both of my solutions all in one simple statement. For this final portion of the lesson, we're actually going to make use of the skills that we learned back in Unit 1, Lesson 4, when we solved equations by factoring. That's the thing we haven't reviewed in this lesson, but we're actually going to look at those skills and try and see how we can use them in some situations in reverse. So let's imagine that we actually already know what the solutions to a specific quadratic equation were. And those solutions we sometimes call roots. So here when it's saying that you're actually given the roots of a quadratic equation, that's another way of saying they're actually telling you the solutions. And actually, these are also equivalent to the x-intercepts if we were to graph this on an xy grid. So we won't worry so much about them being x-intercepts right now. That'll come into play more when we get into some more graphing stuff in future units. But it's really important to remember that roots does mean solutions. So here we're actually going to try and do the process in reverse. We are told what the solutions to a specific equation are, we're going to take them and try and work backwards to build an equation that would produce those roots, which can be a really useful skill for us. There are a lot of situations when we might know specific values for solutions that we're looking for, and we're trying to find the special polynomial equation, or in this case, the special quadratic equation that would make those happen. And we can build that ourselves. Let's see what we mean by that. So here we're given two separate roots. We're told that one of the solutions to the equation is -3, and the other one is 3/4. So in other words, another way we could write that is to say that one solution is an x value of -3, or the other solution is an x value of 3/4. So again, this is why I say we're essentially working backwards, because if I was asking you to solve an equation by factoring, you would possibly get two solutions like this. Now, if you remember, when we solved equations by factoring, we found values like these by recognizing that certain factors must have been equal to 0. So if x is equal to -3, that would be the case only if x plus 3 was also equal to 0. And I just did that by adding 3 to both sides. So I worked backwards from my original root to think about what would be a statement that would be equal to 0 using that root. So now let's do the other one. So if 3/4 is equal to x, then I could multiply both sides by 4, which would give me 4x equals 3, but then I could also subtract 3 from both sides. So 4x minus 3 equals 0. And if you're a little unsure if you found the correct pieces here, work backwards and try and solve them all over again. So if I take 4x minus 3 equals 0, and I try and solve it all over again to get x all by itself, well, guess what? I will get x equals 3/4. And if I start with x plus 3, and I try and solve it all over again to see what x would equal, I will get x equals -3. So now, again, we're just working backwards, but writing equivalent statements. So what does this mean? Well, it means this could have been one factor, and this could have been another factor from the factored form of a quadratic equation. So in other words, if we put this together, like so, a quadratic equation that has this factored form would absolutely have to have these two values as its roots. So now we've actually found an equation that works. So we've worked backwards from the roots to find an equation that would produce those roots. The only last thing we have to do, though, is find it in its full expanded form. So now that we have these two separate factors, we can expand it all out and simplify. So after a little bit of expanding and simplifying, we would get 4x squared plus 9x when we combine a couple middle terms, and then minus 9, all still equaling 0 on the other side. So therefore, that is the equation with the given roots. With roots, again, just meaning solutions. So that's the process. Once again, we start with our original solutions, -3 and 3/4. And then we worked backwards to find separate factors that could each be equal to 0 that would cause those roots to happen. Once we find each of those factors, we put them together in a factored form, and then we just expand it to find the full expanded form of that equation. Let's try one more together. For this last one, we're going to approach it the exact same way and really attack it the same way, but it's just going to look a lot more tricky as we go through, because now, as you can see, it's not just single real numbers that we're dealing with for our roots. We've got roots that have a real part and an imaginary part, so these are overall fully complex roots that we're dealing with. But start it the same way. So if those are our two roots, then it's clear that one of the x values that works is -1 minus 2 root 3i. And while we're at it, x could also equal -1 plus 2 root 3i. So right away, that might look a little bit weird, but again, we can work with it the same way. So now we're trying to take each of those little mini equations that we've set up and rearrange them so that we know what would equal 0 in each case. Well, if I take the one on the left and I move both those terms to the other side, then it would be x plus 1 plus 2 root 3i is equal to 0. Or it's also true that x plus 1 minus 2 root 3i would also equal 0. So let's put that together. And again, it's going to look kind of weird, but it's still going to be technically true. We take all of this stuff and recognize that it could be one big factor in its own bracket. And we take all of this and realize that it will be another great big factor in its own bracket. So it looks something like this. And that technically is an equation that has those two original roots that we were given as the roots of this equation. And from here, we have that very fun task of expanding all of this out and simplifying it. Now, we could just do it term by term in the way that we're used to. So in other words, multiplying every term from the first bracket by every term in the second bracket. But there's also an important thing that we can note here if we look carefully at what we're dealing with. You probably noticed that there's a lot of similar stuff happening in both of these brackets. And so if we break it up by thinking of this first piece all as one single value, so I'm going to call it A. I'm going to imagine that it's something called A. And this entire second piece inside of its bracket, I'm going to call B. So this first bracket is adding those things together. It's adding an A part and a B part together. The other bracket, hey, this is that A value again, and this is that B value again. The only difference with this bracket is that those two pieces are being subtracted. What does this mean? Well, even though it looks really weird, what we actually have here is not just any old factored form, it's a factored form from a difference of squares situation. And so the non-factored form of a difference of squares is where we actually have the difference of squares happening. In other words, we take the square root of, the square of A and the square of B, and we subtract them. So what do I mean by the square of A? Well, the A value was x plus 1. So I take it and I square it. That's essentially like doing A squared. Then the B value, I take it and I square it. So that's like B squared. And all I need to do is put a subtraction symbol in between them, and this is a difference of squares situation. So again, I've just gone from a factored form of a difference of squares, which has A plus B in one bracket and A minus B in the other bracket, and just written it in its more original difference of squares form, which is A squared minus B squared. Now, I have something I can expand out a little bit easier. But it does mean I have a little bit of work to do. So x plus 1 squared, I want to think of that as x plus 1 times another x plus 1. And then in the other one, I really need to square each piece of that single term. So I'm going to have to do 2 squared times root 3 squared times I squared. So can't forget that that equals 0. Now we'll do some expanding of the two binomials. They would eventually simplify to x squared plus 2x plus 1. And then it's going to be minus 4 times 3 times -1. So we're recognizing now that the square of root 3 is just 3. And then I squared is just the number -1. Remember, we've seen that in our previous unit. And that's all equal to 0. So let's simplify even further. X squared plus 2x plus 1, and now everything else just works out to +12. And then those last two things are just numbers and can be combined together. So x squared plus 2x plus 13 equals 0. So we can say something like, therefore, this equation that we came up with in its fully standard form, expanded and simplified, is the equation with the given roots. So keep in mind that if we can solve an equation, a quadratic equation, by factoring and use those factors to find its roots, now you've seen that we can use the roots that we already know to work backwards to find the factors, and then use the factors to produce the full standard form equation. Both will be very valuable skills in future units and later in this unit as well.